Hi, I'm Megan Ruth, and the heat transfer topic that we are going to be talking about is external flow. And external flow is the fluid motion over a flat plate to either heat it or cool it. And the main topic for external flow is forced convection, and this is using either a fan or a pump to blow fluids such as air, water, or oil over your flat plate. And the different boundary conditions that you can have for external flow are either entirely laminar, laminar and turbulent, or turbulent. And you determine these boundary conditions using your Reynolds number. Your critical number is 500,000. And if your Reynolds number is less than 500,000, then your boundary condition is going to be laminar. And if it is greater than 500,000, then the boundary condition is going to be turbulent. All right, so now we're going to look at a problem. So in this problem, we have a silicone chip, and it is being cooled by having air blow over it at 20 meters per second, and air is at a temperature of 24 degrees Celsius, and your chip is 10 millimeters by 10 millimeters, and we are going to find the maximum power or heat rate that can be given so that the chip does not exceed a temperature of 80 degrees Celsius. So what we know is that the velocity is 20 meters per second. The temperature of air, your T infinity, is 24 degrees Celsius. The chip is 10 millimeters by 10 millimeters, or 0.01 meters by 0.01 meters. And your maximum surface temperature is 80 degrees Celsius. And by using the maximum temperature and your T infinity, we can find the film temperature by adding them together and then dividing it by 2. So our film temperature is going to be 52 degrees Celsius. And then from this temperature, and using table A4, we can find the values of Kf, and B and Reynolds number, which we'll need later in the problem. And for this problem, we're also going to assume that it is steady state, that we have constant heat flux, and that there is negligible radiation and heat loss. So that we can find the maximum heat rate. So we're going to start off by finding Reynolds number. So we do RE equals U infinity, which is our velocity, times the length, which is going to be 10 millimeters or 0.01 meters, over V. So we plug in our numbers, and we have 20 meters per second. All right, and then our units will all cancel out. And our RE value is going to be 10,864, and because this is less than 500,000, we're going to have laminar flow. So we can use the laminar condition along with our assumption of constant heat flux to find our Nusselt's number. So we're going to use the equation Nu equals 0.453 times Reynolds number to the 1/2 times Reynolds number, just right there at the bottom, 0.703 to the 1/3, and then Nusselt's number will come out to be 41.90. Unitless. Alright, and so once we have Nusselt's number, we can solve for H, which we are then going to use to find our heat flux, which we can use to find our maximum heat rate. So then we have the equation Nusselt's number equals H times L over K, which we can rearrange to find H. H equals Nusselt's number times K over L. Just plug in our values. Cancel out, and and we get an H value of 118.4 watts per meter squared. Sorry, I let this one cancel out. Alright, and then now that we have H, we can plug this in to find our heat flux. So the equation Q double prime equals H times Ts, which is our max value of 80 degrees Celsius, minus T infinity. Just letting that in. And since that's just the difference, we don't have to worry about our units there between Celsius and Kelvin. And we get EQ double prime of 6,630.4 watts per meter squared. All right. Final steps, we have our maximum power, is we're going to use the equation Q equals your surface area times H, and this Q will be Q max. Right, because the air is just flowing over the top of the chip, our surface area is just going to be that top surface, so it's just 0.01 meters squared, and times H value. Squared cancel out, and we get our maximum heat rate of 0.66 watts, and that's how you solve that. Alright, then last we just have a little real world example of how you can use external flow in the real world that we're probably all familiar with, and especially if you're a student, you probably do this every day at ROMAs. The example that I just used was a toaster oven, specifically one of the kinds that just has a little kind of metal conveyor belt that runs through that you stick your bagel on, it goes in one side and comes out the other. So your bagel's just sitting on here upside, and you need to heat it up, so it's gonna kind of symbolize our flat plate. So we have that it's moving at some velocity into the toaster, and then the air is going to blow over it. And then if you know the temperature of the air inside the toaster and the velocity that it's moving through, you can use that and the temperature of your bagel to kind of solve for TF and get your values, and then you can calculate the maximum power that you wanted depending on how hot you want your bagel to be. So there you go, now we know about external flow.